Okay, let's get started. So today we're going to begin talking about magnetic particle inspection. There are groups of you will have lab today, tomorrow, and Thursday. And so in lab, I'll have groups starting with remote visual inspection we talked about last week. And then I'll also have some groups starting magnetic particle inspection. I'm going to do a demo of this process in lab. I'll do with each lab group. The Wednesday group, I'll probably still split it. With each lab group, I'll do two demos. I'll take half the group in, perform the demo. There's just not enough room in the NDT room to have everybody in there at once. So we'll do a demo and then we'll swap. And next week, the other half of the class will get a demo as well. And then beginning next week, I will also then start to demo liquid penetrant inspection. So groups next week can start working on that as well. So we'll have kind of 3 labs going. And those are those first 3 labs that are going to be kind of the first half of the semester, the first portion of the semester. So magnetic particle inspection, I just have these pictures here so you can kind of see what things look like. So on the right is an object, some kind of object that's had magnetic particle inspection performed on it. And we can see where cracks are showing up, where these areas, we have these kind of defined glowing lines right here. We talked about relevant, non-relevant, and false indications. And so just to kind of discuss those real quick, these cracks would be your relevant indications, right? Looking for those. Non-relevant indications would be things like this is, you have a certain amount of the particles, like on this flange, right? The outside of the prop flange usually isn't machined, it's the raw casting, so it's a rough surface. So you can see some of the magnetic particles kind of sticking to that area. Even though it's not an area of, it's not a relevant, it's not a relevant indication, it is a non-relevant indication. Same thing with like the holes right here, the prop bolt holes. Right, those are going to be non-relevant because that's just where fluid is going to pool. You can't do much about that. It's part of the geometry of the part. And then, there really isn't an obvious false indication here, but if you had something like a fingerprint, if someone had grabbed it or handled it, something like that, or a big drip, you really don't have too much trouble with dripping with magnetic particle. That's more of a liquid penetrant thing, but same thing. To the left of that, we have a penetrant or a magnetic particle bench. So we'll look at what the different parts of that are, how it operates. But this part right here would it'd be held between these two, kind of what are called head and tail stock, in order to perform the inspection. And this is a bench that it can run current through the part. It can run current around the part to create a magnetic field. And then in the bottom, it's got a sump area that's filled with the carrier fluid and the particles that are going to be used to perform the inspection. So with most of the methods we're going to look at, we're going to talk about advantages and disadvantages to start things off. This comes into play, where you have to decide what method is appropriate for a given material or a given construction, a given object, that kind of thing. So, MPI is very sensitive to small flaws, okay? The surface, it's primarily used for surface flaws, but it does, and in certain cases, it does have the ability to find shallow subsurface flaws. So shallow subsurface flaws, meaning they're located near the surface, but they may be slightly under the surface. Okay? It's a very fast method. Probably won't think that at first, but someone who's experienced with it can knock out parts pretty quick. It can be used, it's used often in production environments for quality assurance verification on supercritical parts. Requires moderate skill, some basic training and some practice, but it's one of the, I would say, probably the easier methods to perform that requires specialized equipment. It can be semi-portable. The bench that you saw there is not really portable. It's very heavy. It's large. It has to have electrical service hooked up to it. It uses high critical, and so that's not portable. But then there are other versions we'll look at that are portable, things known as yokes and prods that can be taken out into the field. And relatively speaking, it's inexpensive. Again, that bench is going to be a little bit more expensive. Typically, those benches are used in a production environment. What I mean by that would be like a back shop or a shop where they're doing testing over and over. Whereas the yokes and prods that I mentioned that are portable, they're also, you know, relatively inexpensive. In many cases, less than $1,000 for a set, which in aviation, less than $1,000 is like, you know, nothing. We spend tens or hundreds of thousands or millions of dollars in an MRO or an airline without even batting an eye. So $1,000 is, you know, that's a rounding error on, you know, when all the numbers come to be. So inexpensive in that regard. You know, for a college student, that's, you know, probably a month's rent at least, maybe not. I don't know what our rent's at now. Maybe it doesn't quite cover rent, but disadvantages, however, so magnetic particle means that our part has to be ferromagnetic, right? It has to contain iron. And it has to have the ability to become magnetized or at least to be temporarily magnetized. There are cases where you can use magnetic particle inspection on stainless steel parts. It's not always the best method for that, but because when you are running a current through a part or you put a stainless steel part in a magnetic field, there will be magnetism in the part, and we'll look at what magnetism is. But you obviously can't do something like aluminum or titanium, you know, or some of those other metals that have no ability to magnetize whatsoever. You have to access the entire part, for the most part. Some of the portable stuff you don't necessarily have to do, but you do have to be aware that if it's installed somewhere, or if it's attached to something, you don't want to damage whatever it's attached to. You don't want to cause like arcing or anything like that. Again, it's a high current process. When we're magnetizing a part, this carries some risk of overheat and or welding. There's a couple ways there. So when you run current through a part, or when you run AC current or DC, but you run a current, you get a magnetic field. Magnetic fields can induce a current in a part. It can also cause a part or material to heat up. And this is how an induction furnace works. You probably are aware I worked in the forging industry for a while. The furnaces we used there were induction. They had an induction coil that steel was run through. And when it went in one end, it was cold. And when it came out the other end, it was 1400 degrees. And that's purely from a collapsing and expanding an AC magnetic that would cause the excitation in the part or in the billet before it was made into a part, and it would heat up. And not only 1400 degrees is about where we wanted it, but it did have the ability, if you turned up the current too high, to liquefy the steel. You can actually use it for melting it as well. So, you know, we want to be careful that we don't cook our parts in the process. We don't want to overheat them. Even if we don't melt a part or arc a part, overheating it, what can we damage by overheating something? Where is heat used in steel parts or titanium? It's that tempering or hardening, right? So if you overheat a part and cool it improperly, you can ruin temper, you can ruin case hardening or things like that. So it may not ruin the part in an ability where we can see, but it may change the properties, right? The hardness and the strength of that part without us even knowing it. The welding is usually when a part's put in the bench, if you don't have a good contact, when you're going to run current through the part. If you have poor contact on one of the ends, it's a lot of current, it's going to arc from the contact pads to the part, and then you get burn spots and things like that. When you're done, you have to demagnetize the part. This is important, whether you're in aviation or not. Any ideas? Why would we not want magnetized parts? There's kind of two big reasons, yeah. So it can mess with instrumentation on the aircraft. For parts magnetized, particularly things that are sensing the magnetic field. You know, the one everyone is aware of is like the little whiskey compass, right? But also if you have an aircraft that has what's called an AHARS system, attitude heading reference system, those have flux gates in the wings. You have a flux gate in each wingtip. A flux gate is basically a coil of wire that senses the Earth's magnetic field. And so if you put magnetic parts near those, or if they're near, say, like the landing gear components and they're magnetic, or something like that, or a flap track that didn't get demagnetized, then it can throw off the AHRS, the Attitude Heading Reference System, which is the primary navigation instrument for aircraft, for many, many commercial transport aircraft. If you're trying to do something that's painted, you pretty much have to remove the paint. Part of that too is if it needs to be able to get a good current contact, right? Paint is a bad conductor, it's an insulator. And then at the end of the day, there is a visual element to it, right? We're going to be looking at the part. We're going to have to, your visual acuity is going to play a role. You're going to have to be able to see those indications. You're going to have to make out the indications that sometimes can be hidden. You know, if you have pooling fluid, sometimes it's hard to see cracks in a bolt hole like that, right? You might be able to see it. You might see kind of the pooling fluid, and then you'll see a definite line inside of it. But it's harder to see than these ones that are obviously out in the open like this. These are very easy cracks to see. And these are very large. A lot of times what we're looking for is very, very small. Not only is it a narrow crack, but it's very short. Right? These are long cracks that go all the way around this crankshaft flange. You're going to be looking for these in your lab. We have a bunch of crankshafts that you're going to process with magnetic particle inspection. So visual detection is required. The other part of that, what else do we have to do when we're performing visual inspection? What ultimately are you doing as a technician performing NDT? What is your role at the end there? Determining serviceability. Airworthy aircraft parts, we're looking at serviceability. Okay, so determining serviceability. So then you're going to make a judgment call, right? So not only is it your vision required, but you have to make a judgment call at the end. Some of the tests we're going to do later, they're a little bit more, there's a little bit, some of that error, some of that human factor is taken out. It can be a little bit more automated, or it is already automated. So just a quick review, ferromagnetism. You know, when we're talking about magnetic parts, these are the materials that can be magnetized. And so this part right here is currently demagnetized. What we're looking at is when you have magnetic fields of the various atoms and the various crystalline structure in the part, if the fields are all pointing in different directions, they essentially all cancel each other out, right? So what I mean by that, you know, if you got a bunch of pieces here, right? Say these little boxes are all the parts of the thing. And if you have one that's magnetized south on the left, north on the right, another one's magnetized north on the left, south on the right, their fields are going to cancel each other out, right? Say one is north on the top, south on the bottom, south on the top, north on the bottom. Those two are going to cancel each other out. So when you have a totally random array of millions or billions of little tiny micromagnetic fields that are all in different directions, statistically speaking, they're all going to cancel each other out, right? Because no likelihood for every one that's pointed to the right, there's another one pointed to the left. For everyone pointed up, there's one pointed down, one pointed at 3 o'clock, there's one pointed at 2 o'clock, there's one pointed at 7 o'clock, right? So when we magnetize a part, we align those fields. So now if we take our part and we put it in a magnetic field, we run either a current through it or put it in a strong magnetic field. That's going to take all those fields that were in there, and it's going to cause them to align, right? And so now our part that I have drawn on the board, or what you see here, where the poles are all aligned, now you're going to have a definite north pole and a definite south pole to your part, right? And that's going to cause these flux lines, which are just the magnetic field, right, is going to get stronger. And it's going to be strong enough that it actually forms around the part. It creates that. And so that's that magnetic field that you experience when you're playing with magnets, right? That's when you try to put two magnets together, where if you try to put the north poles together, they try to push each other apart, right? That's this flux field that's doing that. If you put a magnetic field towards a north end of a magnetic field towards the south end of another magnetic field, they're going to try to draw together. They're attracted to one another. That's this flux field that's doing that. And so magnetic particle inspection relies on this ability to do it. And like I said, with ferromagnetic parts, once we magnetize them, they tend, it depends on some factors, they tend to stay magnetized. So that's where we have to demagnetize it when we're done. We have to re-scramble this magnetic field when we're done so that the part is no longer magnetic. Something like stainless steel, in a lot of cases, the poles will align while the magnetizing force is present, while we're running current through the part, or while we're putting the part in a strong magnetic field. But as soon as we take that away, they re-scramble on their own. Okay. So flux, as I've talked about, is induced by passing electricity through or around a part. When we do it around the part, that's creating a magnetic field that's going through the part. Okay, that's our magnetizing force. And it's going to have an orientation and a direction. Like I said, there's going to be a definite north and a definite south. If we create a magnetic field by running a current through the part, or if current's running through an electromagnet that's oriented differently to the part, the field is going to be 90 degrees to that current flow. And that magnetic field that we're inducing in the part will be strongest while the field's being applied. As soon as we shut the field off, it will actually drop. Some of those little individual, fields caused by individual crystals or atoms, they will rotate, but not all of them will. The majority of them will stay aligned with each other, and that's where we get residual magnetism, where the part stays magnetized. A part that has low residual magnetism, stainless steel, there's a larger component that are gonna scramble on their own. So units of how strong this magnetic field is measured in a unit called a Gauss. A Gauss is a unit of the magnetic field. I don't even have a good way of describing it beyond that. Like when people ask me what a Gauss is, it is the unit of magnetic flux, how strong the field is. And if there is, now what you can see here is, well, at the bottom, flux will leave a material if there's a discontinuity in the material. This is known as flux leakage. The magnetic flux will jump off the part. Now, let's go back. In a magnetized part that is coherent, where there's nowhere for it to jump, the field is still jumping, right? It's jumping from one end to the other. It's jumping from the North Pole to the South Pole, or South Pole to North Pole, however you want to look at it. Okay. But if we get a discontinuity or break somewhere in the part, you will also experience a little jump of the magnetic field from one side to the other. If you get a crack in the part, that magnetic field will jump from one side of the crack to the other. And it will leave the surface, kind of like what's happening here. When it leaves the surface, if we apply very, very fine magnetic powders, they will stick to that magnetic field. And if we dye those magnetic powders with a fluorescent dye and then point a black light at it, or if we dye them with colors in certain systems, for visible light, then we can see where those particles collect. And that is the idea behind magnetic particle inspection, is where we get that flux leakage. That flux jumping off the surface of the part is going to cause a stronger magnetic field in that area. And the magnetic particles that are either visibly dyed or are fluorescently dyed, have a fluorescent coating or a visible coating on them, will gather in that area. And then we can see where those particles are gathering, and it tells us that there's some kind of a discontinuity there. It could be a feature of the part, such as that rough surface, or it could be a crack to give us a relevant indication. So here's kind of a diagram of that, how the magnetic flux is oriented. So here, and this is known, many of you probably heard of the right-hand rule before. So if we have current running through this wire, you point your thumb towards negative, and the flux field is going to be, in this case, counterclockwise around that wire, looking at it from the top. If we look at it from the bottom, it's going to be clockwise. But looking at it from this orientation, that right-hand rule is going to create kind of a barrel of magnetic flux around that wire, or in the direction that it's going there. Now, for our purpose, we don't really care which direction it's going. Okay, in fact, we're going to be using an AC, alternating current, mag particle equipment, and so ours is going to flop 60 times a second. Because the electricity running in the US power grid is 60 hertz. If you go do this in Europe, it'll flop 50 times a second. At the end of the day, that doesn't really matter to us much. We just know that. So we aren't too worried about which way the field ends up being. You know, if I let go of the button that sends current through the part, at this fraction of a second, it may be oriented one way. If I hold it 1/60th of a second longer, it'll be oriented the opposite direction. It doesn't really matter, but the part's magnetized at that point. So here are those magnetic properties that I was kind of referencing when I was talking about, can a part be magnetized? A ferromagnetic part, will it be magnetized? So the first one is permeability. So how easy is it to magnetize a material, right? How easy is it to take all those different poles and get them to align with one another? Okay. The next one is reluctance. How resistant to magnetism is a part? What do you notice about reluctance and permeability? They're opposite, they're inverse. So if a part has high permeability, it's easy to magnetize. It means it has low reluctance. It's easy. It has low resistance to magnetism, right? If a part is not permeable, or if a part has high reluctance, if its reluctance is high, meaning it's hard to magnetize, then it's going to have low permeability. So they're inverse to one another. Okay. Flux density. This you can think of as the strength of the magnetic field. And we can look at it from kind of a visual perspective, lines of magnetic force per unit area. Or that area is two-dimensional. It can also be lines of magnetic force in like a cubic space, right? In a three-dimensional space. So how strong is that? The higher the flux density, the stronger the magnetic field, right? A stronger magnet's going to produce a higher flux density. A weaker magnet's going to produce a less strong. When we're dealing with particularly electromagnet, but it can even be a permanent magnet, like a horseshoe magnet or something. Our magnetic, or our magnetic force, what are we using to magnetize the part? That can be a electromagnet, a coil of wire we run current through. It can also be something like a permanent. When we put that near an object, in order to magnetize that object, residual magnetism is how strong or how much magnetic force is left when that magnetizing force is removed. With an electromagnet, that means we shut the electromagnet off. Now it just becomes a coil of wire without any current running through it. If we're talking about a permanent magnet, that means we physically move the permanent magnet away from whatever it is we're magnetizing. How many of you have used, say, a permanent magnet to magnetize something just for fun or for purpose? What do you do? What's an example? What's one we use in aviation? What's one handy in aviation? Anyone know? A screwdriver tip. What do you do with a screwdriver? You can hold the screw on. So you take a screwdriver and you take like a horseshoe magnet and you run it down it a few times, keeping the magnet in the same orientation. You will create a weak magnetic field in your screwdriver. So then you can put a screw, if you have a magnetic screw, a lot of aviation hardware is not magnetic, unfortunately. But if you have a magnetic screw, then you can kind of stick it. It works really well with like Phillips head screws. You can stick it on the tip of the screwdriver, and that little bit of magnetism will help you hold it on the tip of the screwdriver so you don't drop it down into the avionic or the electrical panel or something. The problem with electrical panels, a lot of times the screws you're working with are brass or copper, which don't stick. So then you got to use sticky stuff. So residual magnetism, what's that magnetic force left afterwards once it's removed? Retentivity is the ability of a material to hold magnetism. Okay, so that brass, that bronze, that aluminum, that titanium, they can be in a strong enough magnetic field, they will exhibit magnetism, but as soon as you remove that magnetic force, they will go back to not being magnetic anymore. So they have a low retentivity. Okay, and then coercive force, force required to remove the magnetism. So if you have something with a high retentivity, something that will stay magnetized, and you want to demagnetize it, like if you want to demagnetize your part before you put it back in the airplane, how much coercive force do you need in order to do so? Okay. Going back real quick, one other item, we talked about magnetic parts on airplanes. So one being throwing off navigation. The other one I meant to say, what about an engine part? Why don't you want an engine part to be magnetic? What's the problem with like that crankshaft staying magnetic when we're done? If that crankshaft wasn't cracked and we're going to use it again, why would we want to demagnetize it before we put it back in an engine? So hand kind of going up. I'm not going to say names because I'm recording, so I don't want people to. No, you kind of did the.
Is that anything to do with TV?
It does have to deal with rotation. The rotation can cause an issue. What do we get inside of engines when they run, particularly when they're brand new or when they've been overhauled? Okay, we use mineral oil for break-in. What is that engine going to create or produce during that period of time? You're going to get metal shavings or dust, right? So if you get some steel wear, right, and you have a crankshaft that's magnetized, where is that going to end up? Going to get stuck to the crankshaft, and particularly if it gets stuck inside the journal bearing areas, now it's going to grind between, the crankshaft and the journals, right? Or say you have like a lifter, a valve lifter, right, that has to slide in a tight open. If something's magnetic there, you don't want to jam the lifters up or scrape those up, right? Or a cylinder, you don't want a bunch of metal sticking to the walls of the cylinder and gouging the cylinder, right? So, and turbine engines, we have similar types of things going on. So we want that oil to flow, or we want those particles to flow in the oil to go to the filter and get filtered out, not get stuck in an area where they're going to sit there and grind and grind and grind and grind and grind and cause like bearing failure. So, retentivity, coercive force, those are also inverses of one another, right? Something that's high retentivity, I guess kind of invert, it requires a high coercive force to undo the magnetism you've got. So we can look at this on something called a hysteresis loop with a flux density curve, where it's located. So what this is, where we get going on here, is the x-axis from negative H to positive H is the magnetizing force. In our case, that magnetizing force, we're going to be using an electromagnet, so it is directly related. It is the current level that we're going to run through the part or run through the coil surrounding the part. Right? So the higher the current, the stronger the magnetic field that's going to develop. Okay. Now going up and down, that's our flux density created by the part we're magnetizing, or the flux density exhibited by the part we're magnetizing. Right? So high and low. Now, high, again, in our case, we don't really care which direction. This is showing an AC system like we're using, right? Our voltage is going to be positive, and then it's going to go negative, and then it's going to go positive, and then it's going to go negative. It's going to do that 60 times a second. And at the same time, our flux density, our flux field is going to be pointing one direction, then it's going to flip the other direction. It's going to point one direction, it's going to go back and forth 60 times a second. Okay. And so what's happening here is if we start with a part that is not magnetized, we're going to start at the origin, and that's this vert stack. So as current builds, as our magnetizing force builds in, we'll call it the positive direction, one direction, right? Our flux density is going to increase, and it's going to increase until it gets to a point here, and you can see called saturation. And there's a saturation up here. You can also saturate it in the bottom. What do you think is happening at the saturation point? What does that mean? Can't get any more magnetic. Why can't we not increase the strength of the magnetic field anymore once we reach the saturation point? If we keep turning our current up, this is just going to keep going this way. It's just going to keep going to the right. What has happened at the saturation point that's going to limit it? Yeah. Not necessarily overheat. What has happened at the saturation point? So remember, our part's made up of all these different particles with poles. All the poles have aligned. So this part right here is at the saturation point that I have on the board, right? All the south poles are on the left, all the north poles are on the right, and we've aligned all our poles. So that is the saturation point. So it doesn't matter if we try to force more current through the part or increase the strength of the magnetic field around the part. it's not going to produce any more magnetism than it already is because the individual poles are aligned. So what we want to do when we're magnetizing a part is we want to get it to that saturation point by turning up the current. So we could just crank our current really high for every part, right? And make sure we get saturation. Why can't we do that? I'll go back over here. Why can't we just turn the current up really high? And to make sure we get saturation on every part. Why can't I run a little, a little push rod at the same, or a camshaft at the same current that I do a big honking crankshaft? What's going to happen? I'm going to overheat my part and potentially melt it, probably cause heat damage before I melt it, right? So a smaller part's going to have less, it depends on material property, size of the part, right? For a given alloy that has a certain permeability and ability to be magnetized, the size of the part's going to play a role in how much current or how much magnetizing force you need to reach that saturation point. Now, as soon as that current is, now our magnetizing force, our current, now is going to flip to the negative direction, right? 60 times a second. So as soon as it does that and starts to come back, it'll hit 0 for a second. So I'm going to draw, what I mean by this, remember AC, right? Here's our AC wave, right? Okay, so that's at the point we're probably going to hope to meet somewhere just before here, right? Just before we reach that max voltage, right? So now when we get back where the voltage is effectively 0, which is a small fraction of a second, right, in an AC system, we can say our force is off for a 60th of a second here, right? We're still going to have magnetism. This is exhibiting retentivity, right? Most of those individual poles in the part are aligned, but not quite all of them. A few of them have started to scramble because they're not being forced into that position of alignment anymore. Okay, that's your retentivity. And then as we start to go negative, we'll need a certain amount of magnetizing force in the opposite direction, a certain amount of voltage in the opposite direction, right? We'll actually bring that magnetic force that the part's producing back down to 0. That point C right here. That's our coercive. So coercivity is how much force in the opposite direction do we need? This distance from the origin to C. How much force in the opposite direction do we need to do to get our part to that 0 point, right? And then we start continuing on the downslope of our AC wave. And again, we'll reach now the negative saturation point sometime, hopefully just before we hit our max negative voltage, right? And then the whole process starts again as our voltage goes back to 0, we hit 0 here. And we get to point E, which is our negative, our retentivity in the opposite direction, which is going to be the same. It should be the same distance from the origin each way, right? Parts aren't necessarily easier to magnetize one way than the other, right? And kind of the same thing then as that voltage starts to go positive again, it's going to pull us up to the coercive direction in the movement from negative to positive field, right? And you can see the distance, the X distance there, or H distance from origin to C and origin to F are about the same. It takes the same amount of current going the opposite direction to get there. And then as it continues to rise, we'll start the cycle all over and reach that positive saturation. It keeps going. Right. So every time we're putting a part in and doing that, it is going to go through those various areas. Now, the nice part is this is happening 60 times a second. It's only at one of these any fraction of a time. If we apply a magnetizing current, an AC current, and we release that button, because this is happening so quickly, most of the time we're going to be somewhere between B and A and B, or we're going to be between D and E. And so we're going to end up, when that current's removed, we're going to end up at the saturation or at the retentivity point. Right? We won't have quite the same magnetism we have when that voltage, that magnetizing force, the voltage is at its max. but we'll have pretty close. We'll have, 80% of that. Okay, which is enough to make those little magnetic particles stick to the part. Depending on the part, something like stainless steel, it'll have a saturation point. The retentivity point is going to be pretty darn close back to the origin. Right? It's going to have a real steep return curve, right? Because it loses magnetism. Something like soft iron, it retains a lot more. In fact, that's our next slide right here. So soft iron has high permeability. What's permeability mean? Easy to magnetize, right? Soft iron is easy. Okay. What does reluctance mean? It has low reluctance. Resistance to magnetism, right? So it's easy to magnetize, has low resistance. It creates a very strong magnetic field, high flux density. Okay. It's also fairly easy to, it has kind of a low residual magnetism when we just apply it. Now, I think I just kind of changed what I said. Here I was looking at this curve as a whole going back and forth, where we start to get negative. If we just apply this positive, get it to saturation, remove it, just like it was easy to magnetize, it's going to drop quite a bit. It doesn't hold on to as much. Okay. It doesn't retain as much, but it also doesn't take much to lose its magnetism. Something like hard steel, and stainless steel is typically your hardest steel. The more carbon you add, the harder the steel. Is going to have low permeability. It's going to be very high to get it to do it. Now, the thing though is once we get it magnetized, if you can get it to magnetize, that's the hard part. With a lot of stainless steel parts, the current needed to reach saturation is higher than the current that the part can handle. Okay, that's where our problem comes in. You need a lot of current, a lot of magnetizing force to get it to do it. But once it is magnetized, it's very difficult to demagnetize because you need the same reverse current in order to demagnetize it, in order to pull it back the other direction. The other part of that, there's another piece, is that parts that are hard steel, what's another way to demagnetize something? You're familiar with another method that can potentially demagnetize that? Percussion, hitting it. And so you have that as well. It doesn't do well when you hit it. So here's some illustrations of how this process works. I described it. Let's kind of see it. So here's a permanent magnet. So rather than using an electromagnet, we're going to do a permanent magnet. When we put a permanent magnet next to a ferromagnetic part, that flux is going to travel through the part. This could also be an electromagnet putting flux into the part, right? And so here's just that part showing that magnetic field running through it. And that's called flux leakage that occurs at a crack. So that field jumping across the crack. And when the field jumps across, those magnetic particles are going to stick in that area. And that's those indications of cracks or flaws or other items. Or again, it doesn't have to be a relevant indication. It can be, a rough surface is going to cause the magnetic field to jump. A corner in a part, 90-degree corner, you're going to have flux jumping across the corner. So you tend to have magnetic particles gathering down in a corner, an inside edge, or in a hole, like the bolt holes you saw at the very first slide. There's a magnetic field jumping across those bolt holes. So not only does the fluid tend to pool there in the first place, but there's a magnetic field that's stronger inside that hole than there is surrounding it. So now we're going to look at the process. And today I'll demonstrate the process for the first lab group, tomorrow and Thursday for the rest. Okay. But we have a just general process. The first thing we do is our part needs to be clean, magnetize it. We'll apply particles. We kind of do the magnetizing the particles at the same time. We're going to do a method called wet continuous, which is the accepted method for aviation. That means we apply the particles in a fluid bath, a carrier solution, while we're putting the magnetic force in the part. After that, we're going to check the magnetic field to make sure that there is a residual field present. And at that point, then we can inspect the part. And this is important that we check for residual field. And we make sure our part has some magnetic field so we know that the particles are going to stick. When we're done inspecting it, we may, and you may redo this. In fact, you're going to redo this a couple times. You're going to go through the cycle because we're going to magnetize it a couple different directions. Sometimes you may need to physically turn your part over to see a different area of it. And so you may have to do this, once you've inspected it, then you remagnetize. You don't have to demagnetize it every time. If you magnetize it with current running in a different direction or in a different orientation, that we're using a strong enough current, it's just going to undo whatever you did the first time and do it right, do it the direction you want the second time. Okay. What we've done, then you'll demagnetize the part. We'll check our magnetic field again to make sure that the magnetism is gone. And we'll need to clean the part because we're going to have carrier solution and particles all over it. And then you're going to report your results. Okay. Homework. All right, the reported results. So cleaning the part, it's essential that our particles have unimpeded access to the flux that is leaking, the flux field that is leaking from the surface of the part. And so in order to do that, we got to make sure that there's no contamination on the surface. We don't want a bunch of grease or oil, the grease and oil can get sticky, having the particles get all stuck in that stuff, right? We also don't want it to be thick enough. Grease and oil can actually be thick enough that the magnetic field jumps inside of it, but never comes to the surface. Right? This magnetic field with little tiny cracks, it's not jumping very high off the surface of the part. Right? And so if you have a thick enough layer of grease or even paint, that field may never make it to that surface. Right? It leaves the surface of the metal structure, but it never gets above whatever's on the metal. And so we have to remove those. Cleaning materials such as solvents or detergents, however, also have to be removed and dried beforehand. We don't want the cleaning solvent breaking down the carrier solution. Right? If we use alcohol to clean our part, our carrier solution is petroleum-based. You put a bunch of alcohol, alcohol into a petroleum product, it's going to break it down. That's the whole point. We use alcohol to clean it, to get rid of oily stuff. And so things like that, we got to be careful. The carrier solution is very similar to mineral spirits, but it's not exactly the same as the mineral spirits that's in our wash tanks. So we don't want to be introducing the mineral spirits into our carrier solution and have it potentially react with the magnetic particles or do something funky there, right? It has a certain viscosity. It has a certain lubricating property. It has a certain, thing to be able to carry those particles correctly. Okay. I'll go with the next two slides and we'll call it good. So magnetizing the part, the direction of the field is important to determine cracks. What I mean by direction is not north or south. Okay, what I mean by direction is, so our part I drew on the boards, the field here is jumping from left to right, right? So if I have a crack running vertically in my diagram, and we've got fields running this way, it's going to jump across it. But if I were to have a crack in a top surface going this way, that's parallel to the magnetic field, it's not really going to jump, right? So what I have to do is I then have to magnetize my part 90 degrees to that. So now my field on my example here is running vertical, and now it would cause it to jump across cracks. So for most things, most parts, you have to magnetize it in two different directions. That's why we have the head and tail stock that can run current left to right. It gives you a circular field. And we have the circular ring that causes the magnetic field to run left and right. Okay, that 90 degree. So circular and longitudinal current flow are used to do those 90 degrees. The current required will be specified by the part. That usually comes from the part manufacturer based on its size and the material it's made out of. You have to kind of use trial and error to find the current we're going to use. Start low and increase it till you reach a desired amperage, because the size of the part's going to affect, the resistance of the part's going to affect how much current for a given voltage you end up with. And then we're going to check the part to make sure it's magnetized. And we're going to use a Gauss gauge like this, or a Gauss meter, to be sure. Now this only reads a changing magnetic field. So if we have a part that's sitting there that's magnetized, and I bring this up and I just put it next to it, what's going to happen? Doesn't read anything. We have to actually be moving it next to the part so that there's a magnetic field. By moving this around, it's gonna feel a change. That magnetic field, as it moves closer and further away from the part or different features, it's gonna do that. And the stronger the magnetic field in the part, the more deflection you're gonna get on this based on moving it. Now, if you move it faster, it'll also get more deflection. So you always want to kind of move it at a and I don't know how to describe it, a kind of a normal pace. You don't want to be sitting there. And if you shake it around anyways, the little pointer is going to be wobbling all over. It's mounted on a spring anyways. So, okay. So we'll leave off there and we'll look at the test bench, the rest of the process in the next time.